At 48 minutes past midnight on Friday morning, 5 volcanoes in the Cascade Range heard something explode. Glacier Peak, Rainier, Adams, St. Helens, Hood. Instruments installed to listen for eruptions all registered the same pressure wave rolling across Washington state, and what made it was not a volcano. It was a piece of an asteroid, coming apart 28 miles above a wheat field with a force of 10 tons of TNT, bright enough to wake people across 3 states and a Canadian province. NASA has already ruled out the obvious explanation. It was not a Perseid, which means it came from somewhere nobody had catalogued. And when you work out which direction it actually came from, the answer lands somewhere that should not be comfortable. So hit like and subscribe to the Skylab, because this story gets one news cycle and then quietly develops for months. Drop a comment telling me where you were watching from and whether you saw it, heard it, or slept straight through a rock exploding over your state. Now, let's get into it. Part 1. The Flashover Soap Lake. At 48 minutes past midnight, Pacific Daylight Time on Friday the 14th of August, 2026, the sky over central Washington state turned white. It was not lightning. There were no storms in the Columbia Basin that night. The air was clear and dry and the moon was nowhere near full, and across 4 separate jurisdictions in 2 different countries, people who happened to be awake looked up and saw something that did not belong there. In the space of a few seconds, it crossed a large fraction of the sky, brightened until it threw shadows, and then it was gone. Some of them heard it afterward. That part came later, and it matters more than you would think. In Coordinated Universal Time, the moment was 07 hours, 48 minutes, 33 seconds. That number is precise for a reason, and we will come back to it, because the entire question this video is built around turns out to depend on knowing exactly what time it was. Here is what we know, and I want to give you the answer early rather than making you wait for it. The object that produced that flash was a piece of an asteroid. NASA's Meteoroid Environment Office puts it at roughly 16 inches across and roughly 170 pounds, something about the size of a beach ball, weighing about as much as a grown adult. That is the whole thing. That is what lit up parts of 3 states and a Canadian province at 1 in the morning. And here is the second half of the answer, delivered just as plainly, because it is the fact that turns an ordinary light in the sky into a genuine mystery. NASA's assessment includes one sentence that most of the coverage skipped straight past. It reads, and I am quoting it exactly, "This fireball was not part of the Perseid meteor shower. It was a background sporadic meteor." Sit with that for a second, because the word doing the work there is sporadic. A meteor shower is a known quantity. The Perseids come from a comet called Swift-Tuttle. Earth crosses that comet's debris stream on the same dates every single year, and astronomers can tell you months in advance roughly when the peak will fall, roughly how many meteors an hour you should expect, and exactly which patch of sky they will appear to come from. A shower meteor has a return address. A sporadic does not. A sporadic is a rock that was not part of any catalogued stream, on an orbit nobody had ever recorded, arriving on a schedule nobody knew existed. It is the background. It is the constant, low, unremarkable rain of debris that has been falling on this planet since before this planet had oceans. And almost all of it goes unnoticed, because almost all of it is the size of a grain of sand, and almost all of it burns up over water in the middle of the night. This one did not go unnoticed. The numbers on the entry are unusually specific, which is itself part of the story. The object first became luminous at an altitude of 77.9 kilometers. That is 48.4 miles straight up, which puts it well above every aircraft, well above every weather balloon, and comfortably inside the region of the atmosphere where the air is so thin that you would call it vacuum if you were not being careful. The position was 47.412 degrees north, 119.412 degrees west, and if you put those coordinates into a map, you land on a small town in Grant County, Washington, called Soap Lake. Soap Lake has about 1,700 people in it. It sits at the southern end of the Grand Coulee, in the shrub steppe country east of the Cascades, in one of the strangest pieces of terrain in North America, carved out by catastrophic glacial floods at the end of the last ice age. It is a quiet place. And for a few seconds on Friday morning it was directly underneath the beginning of something. The speed was 14.6 kilometers per second. NASA rendered that figure for the public as 32,800 miles per hour, and most of the news coverage rounded it to 33,000, which is where that number in the headlines came from, and the direction was north. I want you to hold on to that one because it is going to matter more than anything else in this entire story. Not the size, not the mass, not the energy, which is the number everybody repeated, the direction. Everything else you're about to hear is an estimate wrapped in an assumption. The direction is the one clean measurement in the whole event, and by the end of this video you are going to understand why that single fact points somewhere genuinely strange. The event carries two catalogue numbers because two separate organisations logged it independently. NASA's Meteoroid Environment Office filed it as Event 202608114-074833, which is simply the date and the time run together. The American Meteor Society filed it as Event 6582 of 2026. Two identifiers, 1 4-second window. The reports came in from a wide area, Washington state obviously, the Columbia River Corridor, northern Oregon, Idaho, and north of the border in British Columbia. That is a viewing footprint several hundred miles across, which tells you something about the altitude because you cannot see something that is only 40 miles up from 400 miles away. The curvature of the Earth gets in the way. You need height, and this thing had height. The spokesman Review reporting on the Friday put the count at nearly 250 reports filed with the American Meteor Society. By later that same day, the figure circulating had climbed to 266. Both of those numbers are correct, and the difference between them is not an error. Fireball report totals climb for days after an event, because the way most people find the reporting form is by searching for what they saw the next morning, or the morning after that, or after a friend mentions it. The count is a measurement of public awareness as much as it is a measurement of the sky. The man who runs that reporting system is named Robert Lunsford. He is the Fireball Program Monitor at the American Meteor Society, which means that when several hundred people file accounts of a light in the sky, he is one of the people who has to turn that pile of descriptions into something resembling a trajectory. He has been doing it for a long time. He's not easily impressed by a bright meteor. His reaction to this one, on the record, oh man, it put on a show. He was also, in his own word, flabbergasted. Not by the fireball itself, but by how many people saw it. 250 reports is a normal haul for a daytime fireball over a populated area, when everybody is already outside and already looking around. This one happened at 48 minutes past midnight on a weeknight. Almost nobody is outside at 48 minutes past midnight on a Thursday going into a Friday. And yet the reports poured in anyway. One of them, Lunsford noted, came from a man who was watering his lawn. I want to point out what that number actually proves, because it is doing quiet work. You do not get 250 independent reports in the middle of the night from something faint. The report count is an indirect measurement of brightness. It means this object was bright enough to pull people's attention through windows, through closed curtains, off their phones, and out of whatever they were doing. It lit the ground. We know it lit the ground because of the cameras. In Spokane Valley, more than 100 miles east of the entry point, residents woke up, checked their security footage, and found the flash sitting there in the recording. One of them told the spokesman Review that her first thought, seeing the sudden white light on the camera, was that something had happened at her neighbour's house. It took her a moment to understand that the light had come from the sky. She had never seen a meteor before, and she had accidentally recorded one. That story repeated itself across the region all Friday morning. Doorbell cameras, driveway cameras, dash cameras left running. Dozens of households discovered that they had captured a piece of an asteroid without knowing it, because the entire modern world is now passively watching the sky, whether it means to or not. Now, here is the thing that makes almost everyone reach for the wrong explanation. The Perseid meteor shower, the most famous shower of the northern summer, had peaked on the Wednesday night going into the Thursday morning. On the night we're talking about, it was still running hot. Anybody in the Pacific Northwest who saw a bright light streak overhead in the small hours of Friday morning had one obvious, available, entirely reasonable explanation sitting right there. It is Perseid season. It was a Perseid. It was not a Perseid. NASA said so directly, and I read you the sentence at the top, but I'm not going to ask you to take that on authority, because taking things on authority is how you end up with a channel that just reads press releases out loud. Later in this video we are going to work out, from nothing but the published coordinates and the published time, exactly where in the sky the Perseid radiant was sitting at the moment this object appeared, and exactly which direction a Perseid would have had to travel. And when you do that arithmetic, the answer is not close, it is nearly the opposite. Which leaves us with a problem, and it is the problem this whole video exists to chase. If it was not a Perseid, and it was not any other known shower, then it came out of the unlabelled background. It came from an orbit that was never catalogued, from a population nobody is tracking, and the only physical evidence we have about where it started is the direction it was travelling when it died. North. Hold that thought, because the background, it turns out, has been behaving very strangely all year. Part 2, 36 miles. In 4 seconds. The whole event happened inside a band of atmosphere 32 kilometres thick. That is the first thing worth understanding about a fireball, and it is the thing that almost nobody pictures correctly. When you watch the security camera footage from Spokane Valley, your brain reads it as an object falling out of the sky and crashing somewhere over the horizon. That is not what happened. What happened took place entirely between 77.9 kilometres of altitude and 45.5 kilometres of altitude. The object never got below 28 miles up. Nothing crashed. There was no impact in any meaningful sense of the word. The endpoint sits at 47.850 degrees north, 119.408 degrees west, at an altitude of 45.5 kilometres, which is 28.3 miles. Put those coordinates on a map and you land on a place called Sims Corner. It is a crossroads in Douglas County. There is not a great deal there. Wheat mostly, basalt, the scablands. Between Soap Lake and Sims Corner, NASA gives the path length as 36 miles. I ran that independently because it is a useful check on everything else. If you take the published start coordinates and the published end coordinates and the published altitudes and you compute the actual three-dimensional distance between those 2 points, you get 58.5 kilometres. Convert that to miles and you get 36.4. NASA said 36. The internal arithmetic holds. The numbers describing the path are consistent with each other, which is worth noting, because in a few minutes we are going to hit 2 numbers in this same dataset that are not consistent with each other at all. Now, let us look at the direction properly, because this is where the video's real question begins to take shape. The start point is at latitude 47.412. The end point is at latitude 47.850. The difference is 0.438 degrees of latitude, which is about 49 kilometres of northward movement. The longitudes are 119.412 and 119.408. The difference there is 0.004 of a degree, essentially nothing. Run the trigonometry, and the ground track heading comes out at 0.35 degrees. 0 is due north. This object was travelling due north to within about 1/3 of a degree, not roughly north, not north-northeast. North, along a line so straight that if you drew it on a map you would assume somebody had used a ruler. The entry angle falls out of the same numbers. The object lost 32.4 kilometres of altitude while covering 48.7 kilometres of horizontal ground, which gives an angle of 33.6 degrees from the horizontal. That is a shallow to moderate entry. It was not dropping straight down. It was coming in at a slant the way a stone skips across water rather than the way a stone drops into a well, and the difference between those two geometries turns out to control almost everything about what happens next. And then there is the duration. 58.5 kilometres of path, travelled at 14.6 kilometres per second, takes 4.0 seconds. That is the entire luminous flight. 4 seconds. Compare that against what people actually reported. Witnesses described a flash lasting under 10 seconds. Lunsford, describing it to the spokesman Review, said it lasts maybe 5 to 10 seconds at the most, and then added something I think is one of the most quietly useful sentences in the whole story. When you look at the video, you're seeing the beginning and the end of this. A 4-second solution sits comfortably inside a 5 to 10 second impression, and the gap between them is not a contradiction. It is a well-documented feature of how human beings experience sudden, bright, frightening events. Time stretches. 4 seconds of unexpected white light in the middle of the night seen by somebody who had no idea it was coming, gets remembered as 8. This is why witness triangulation is useful for figuring out where something went, and close to useless for figuring out how long it took. So what was actually happening during those 4 seconds? Start at 78 kilometers. Up there, the air is roughly 100,000th as dense as the air you're breathing right now. To a human being, that is vacuum. To a rock moving at 14.6 kilometers per second, it is a wall. The thing that makes a meteor glow is not friction, despite what most of us were taught in school. Friction is what happens when 2 surfaces rub. What actually happens here is compression. The object is moving so much faster than the speed of sound that the air in front of it cannot get out of the way. It piles up. And when you compress a gas violently and suddenly, it heats, and at these speeds it heats to thousands of degrees, hot enough to strip electrons off the atoms and turn the air itself into plasma. That plasma sheath, sitting a short distance in front of the rock, does 2 things. It glows, which is most of what you see, and it heats the rock's surface until the surface begins to vaporize and blow away in a stream behind it. That process is called ablation, and it is the mechanism that destroys almost everything that enters the atmosphere. The rock is not burning in the chemical sense. It is being boiled off from the outside in. The vaporized material streaming off the surface glows too, in the specific colors of whatever elements were in the rock. That is why some fireballs are green, and some are orange, and some are that hard blue-white that people describe as looking like a welding arc. You're watching a mass spectrometry experiment conducted at 33,000 miles an hour by nobody. And as the object descends, the air gets thicker, fast. Atmospheric density roughly doubles for every 5 kilometers you drop. Going from 78 kilometers down to 45 kilometers is not a small change. It is a change of something like a factor of 100 in the density of the medium the object is ploughing through. The pressure on the front face of the rock, what aerodynamicists call dynamic pressure, scales with that density and with the square of the speed. So as it falls, the force trying to crush it climbs and climbs. Every rock has a limit. Every rock has a tensile strength, a maximum stress it can carry before it fails. And for ordinary stony meteoroids riddled with cracks and inclusions from 4.5 billion years of collisions, that limit is much lower than you would guess. It is often lower than the strength of a decent brick. At 45.5 kilometers above Sim's Corner, this object hit its limit. And when a body like that fails, it does not crack politely down the middle. It fragments, and in fragmenting it exposes an enormous amount of new surface area to the airflow all at once. Every one of those new surfaces immediately begins ablating. The energy that had been depositing steadily along 36 miles of flight path now dumps into the atmosphere in a fraction of a second. That is the terminal flash. That is the moment the light curve spikes and the whole sky goes white. That is what the security cameras in Spokane Valley recorded, and it is why so many people described a single, sudden brightening rather than a gradual streak. It is also the moment that made the noise. NASA's assessment states that the fragmentation created a pressure wave that propagated to the ground, and that this is the source of the boom some witnesses reported. Lunsford described the same physics in planar terms. In Spokane, witnesses heard a noise from the fireball, which means a fragment may have blasted down to the lower atmosphere, where air molecules are thick enough to carry sound and create a sonic boom. Think about what that requires. A shock wave generated 28 miles above the ground, in air so thin it barely qualifies as air, has to survive the trip down through the whole depth of the atmosphere and still arrive with enough energy to be audible to a person standing in a yard in eastern Washington. That is not a small amount of energy. We will get to exactly how much energy in a moment, and when we do, we're going to run into the single strangest thing in this entire data set. But keep the through line in view. Everything I have just described, the altitudes, the path, the angle, the duration, the physics of the fragmentation, is a reconstruction. Not one person watched this happen with an instrument that was designed to watch it happen. Every number came out afterwards, assembled from whatever happened to be pointed in roughly the right direction. And the only quantity in that entire reconstruction that does not depend on an assumption about what the rock was made of is the direction it was going. North. Still north. Hold it. Part 3. The rock that was never a Perseid. The wrong answer is attractive because the timing is almost perfect. The Perseids peak in the second week of August every year, and in 2026 the peak fell on the Wednesday night, going into the Thursday morning, the 12th into the 13th. Our fireball arrived in the small hours of Friday the 14th, roughly a day and a half later, with the shower still very much active. If you were standing outside on that Friday morning, you were genuinely surrounded by Perseids, 2 or 3 of them a minute if your sky was dark. So when the big one came, of course, everybody assumed it was one of them. It is the reasonable assumption. It is also wrong, and it is wrong in 4 independent ways, which is unusual. Normally in this line of work you get 1 clean discriminator if you are lucky. Here we get 4, and any single one of them would be enough. Start with what a Perseid actually is. Comet 109P/Swift-Tuttle is a body about 26 kilometers across on a long orbit that brings it through the inner solar system roughly once every 133 years. Every time it comes close to the Sun, it sheds material, and that shed material spreads out along the comet's orbital path over centuries until it forms a long, thin tube of debris looped around the Sun. Earth's orbit crosses that tube in August. We drive through it. What we call the Perseid meteor shower is our planet driving through the exhaust trail of a comet that last came near us in 1992. The particles in that trail are small, most of them smaller than a grain of rice, and they are fragile. They are cometary material, which means they are loose aggregates of dust and ice and organic compounds that were assembled in the cold outer solar system and have never been heated enough to consolidate. You could crush most of them between your fingers. That fragility matters, and here is the first disqualifier. Perseid particles ablate high. They light up around 100 kilometers, they burn out around 80, and no Perseid has ever been known to deliver a fragment to the surface of the Earth. Not one in the entire recorded history of the shower. They cannot survive. Our object reached 45.5 kilometers, generated a shock wave that made it all the way down to people's ears, and left a radar signature suggesting that pieces of it are currently sitting in a wheat field in Douglas County. That is not cometary behavior. That is a rock. Second disqualifier, the speed. Perseids enter the atmosphere at about 59 kilometers per second. Our object entered at 14.6. That is a factor of 4, and the difference is not a detail you can wave away, because entry speed is not a random property. It is set entirely by orbital geometry. The Perseids are fast because Swift-Tuttle orbits the Sun backwards relative to the planets, so when Earth crosses the debris trail we hit it very nearly head-on. The 2 velocities add. Our object came in at 14.6 kilometers per second, and Earth's escape velocity is 11.2, which means that once you subtract out the acceleration, the planet's own gravity gave it on the way in. The object was barely moving relative to Earth at all before it arrived. That tells you something very specific about where it had been. A body that meets Earth that gently must have been on an orbit very much like Earth's own. Low eccentricity, meaning a nearly circular path rather than a stretched ellipse. Low inclination, meaning it was moving in roughly the same plane as the planets, rather than cutting across them. And a semi-major axis somewhere near 1 astronomical unit, meaning it went around the Sun on roughly the same sort of timescale we do. This was not a visitor from the outer solar system. This was a neighbour. Earth caught up to it, or it caught up to Earth, and the encounter was closer to a rear-end collision than a head-on one. Third disqualifier, and this is the one I want to do properly, because it is the one you can check yourself. Every meteor in a shower appears to come from a single point in the sky called the radiant. That is a perspective effect, the same reason railway tracks appear to converge at the horizon. The particles are all travelling on parallel paths, and parallel lines seen in perspective look like they emanate from one spot. The Perseid radiant sits in the constellation Perseus, which is how the shower got its name. So the question is simple. Where was Perseus from Soap Lake, Washington, at 07 hours 48 minutes 33 seconds, Coordinated Universal Time on the 14th of August 2026? I calculated it. At that moment, from that location, the Perseid radiant was 39.7 degrees above the horizon at an azimuth of 43.5 degrees. 43 degrees of azimuth is northeast, and here is what that means physically, and it is the whole ball game. A meteor from a radiant in the northeast travels away from the northeast. It moves toward the southwest. That is the direction Perseids were moving across the sky over Washington that night, and if you have ever watched a Perseid shower from the northern United States in August, that is exactly the direction you have seen them go. Our object travelled due north. That is not a small discrepancy. That is not within the error bars. A northeast radiant and a due north track are close to opposite behaviours, and there is no version of the physics where a particle from Perseus crosses the sky heading north. NASA's one-line dismissal turns out to be independently verifiable from published numbers, and it verifies. The fourth disqualifier is really a mopping-up exercise, because the Perseids are not the only shower running in mid-August. There are two other candidates worth naming, and both of them fail. The Kappa Cygnids are active around this time of year. Their radiant is in Cygnus, which was high in the northern sky, and that puts them in the same category as the Perseids, wrong side of the sky entirely for a northbound object. The southern Delta Aquariids are the more interesting near miss. Their radiant is in Aquarius, which was in the southern sky in mid-August, and southern is at least the right general area. But southern Delta Aquariids enter the atmosphere at about 41 kilometers per second. Our object came in at 14.6, nearly 3 times too fast. Speed rules them out on its own, so every labelled source has now been eliminated, not by assertion but by geometry, by speed, and by what survived the fall. I want to add one thing to the record here, and I want to be careful about how much weight I put on it, because it is easy to overread. In late March of this year, a fireball crossed this exact stretch of Washington and British Columbia at around 39,000 miles an hour, generating over 100 witness reports. We covered it at the time. 2 large sporadic fireballs over the same relatively thinly populated corridor of the Pacific Northwest inside a single calendar year is, on its own, not statistically remarkable. The Pacific Northwest is a big target, fireballs are undirected, and coincidences are the most common thing in the universe. I am not going to stand here and tell you that 2 events 5 months apart constitute a pattern, because they do not, but it belongs in the record, and the reason it belongs in the record is what we're about to get into. Because when you strip away every catalogued source, what you're left with is the background, the sporadic population, the rocks nobody's tracking, on orbits nobody has written down, arriving whenever they arrive. And in 2026, somebody measured that background very carefully and found that it was not behaving the way it is supposed to. They found it in the counts, and the counts were argued about, and eventually the counts were more or less explained away. But they also found it in the directions, and nobody has ever explained that. Part 4. 10 tons of TNT. Everything we know about this rock is a number somebody worked out afterwards, and 2 of those numbers cannot both be true. Let me show you what I mean, because this is the kind of thing that sounds like an accusation and is not one, and I want to be precise about the difference. The headline figure, the one that made every news story and every social media post about this event, is the energy. When the object fragmented at 45.5 kilometers above Sims Corner, NASA states that it released an energy of 10 tons of TNT. 10 tons of TNT is a real quantity, and it is worth making physical before we do anything else with it. It is roughly the yield of a large conventional bomb. If you set it off at ground level in a populated area, you would have a catastrophe on your hands. Set it off 28 miles up, in air that is 1,000th the density of the air at your feet, and something quite different happens. There is nothing up there for the energy to push against. Most of it radiates away as light, which is why the sky went white. The rest goes into a pressure wave that expands outward through progressively denser air, losing energy the whole way down, until what finally arrives at the surface is a low rumble that rattles a window and makes a dog bark. That is why nothing was damaged. Not because 10 tons of TNT is small, but because 30 miles of atmosphere is an extraordinarily good shock absorber. Now let us check the arithmetic, and I would encourage you to run this yourself because it takes about 30 seconds and a calculator. The kinetic energy of a moving object is 1/2 of its mass multiplied by the square of its speed. That is it. That is the whole formula, and it is the same formula whether you're talking about a bicycle or an asteroid. NASA's published mass is approximately 170 pounds. Convert that to metric and you get 77.1 kilograms. NASA's published speed is 14.6 kilometers per second, which is 14,600 meters per second. So, 1/2 times 77.1 times 14,600 squared. 14,600 squared is about 213 million. Multiply that by 77.1 and you get about 16.4 billion. Halve it, and the answer is 8.22 billion joules. Now convert to tons of TNT. 1 ton of TNT equivalent is defined as 4.184 billion joules. Divide 8.22 billion by 4.184 billion, and you get 1.96. The entire kinetic energy of a 170-pound object travelling at 14.6 kilometers per second is about 2 tons of TNT. NASA's published fragmentation energy is 10. That is a factor of about 5, and it runs in the direction that is hardest to explain away. It is not that the fireball released less energy than the object was carrying, which would be completely normal, because objects routinely deposit only part of their energy in a single fragmentation event. It is the opposite. The release, as published, is 5 times larger than the total energy budget of the object as published. The rock cannot spend money it does not have. Run it backwards to see the scale of the gap. If you take 10 tons of TNT as the true energy, and 14.6 kilometers per second as the true speed, and you solve for the mass, you get about 392 kilograms. That is 865 pounds. 5 times the published figure. Not a beach ball weighing as much as an adult. Something closer to the weight of a grand piano. So what is going on? Here is the honest answer, and it is much less exciting than a cover-up and much more useful. Nobody weighed this rock. Nobody could have. The mass in that press release is not a measurement. It is the output of a chain of assumptions, and the chain runs like this. The satellite instrument that recorded the event measured light. Specifically, it measured an optical energy. How many photons arrived at the detector, over what period, at what wavelength. That is a real measurement, and it is a good one. But you do not want optical energy. You want total kinetic energy, and the two are related by a quantity called luminous efficiency, which is the fraction of the object's kinetic energy that comes out as visible light rather than going into heat, into ionizing the air, into the shock wave, or into throwing rock vapor around. That fraction is not measured for any individual event. It is modelled. And the models disagree with each other, sometimes by a factor of several, because luminous efficiency depends on the speed, the size, the composition, and the altitude of the object, and you do not independently know any of those things at the moment you are trying to calculate them. So you assume a luminous efficiency, and you divide, and you get a total energy. Then you take that energy, and you divide by 1/2 the speed squared, and you get a mass. Except the speed itself came from a trajectory solution that was assembled from eyewitness triangulation and a handful of cameras, and it carries its own uncertainty. Then you take that mass, and you assume a density, and you solve for a diameter, and that is where the 16 inches comes from. 3 assumptions stacked, each one multiplying the uncertainty of the last. What you end up with is a number that gets printed without an error bar and repeated as though it were measured with a ruler. You can actually watch the same problem happen inside these two figures. A sphere 16 inches across has a volume of about 0.035 cubic meters. Put 77.1 kilograms into that volume, and you get a bulk density of about 2,200 kilograms per cubic meter. For comparison, an ordinary stony meteorite runs around 3,400. 2,200 is low. It is the density of a porous body, or a carbonaceous one, or a rock with a lot of empty space in it, which is possible and even interesting, but it means the 16-inch figure is quietly carrying a compositional assumption that nobody stated out loud. There is a further wrinkle that makes the gap harder rather than easier to close, and it is worth spelling out because it runs against the intuition most people have. You might reasonably think that the fragmentation figure and the total energy figure are simply measuring different things, and that this explains it. In a sense, they are. But the relationship between them runs the wrong way to help. An object entering the atmosphere does not save all its energy for one moment. It sheds energy continuously along the entire flight path, through ablation, through heating the air, through the shock wave it drags behind it for 36 miles. By the time it reaches its fragmentation altitude, it has already spent a portion of what it arrived with, so the energy released at the terminal flash should be a fraction of the total, not a multiple of it. The published numbers ask us to believe the opposite. There is also a timing point that gets lost in the reposting. Figures like these are preliminary. The Meteoroid Environment Office publishes an assessment quickly, often within a day, because there is public interest and because meteorite hunters need a search area before the weather changes. Those figures then get refined as more camera data surfaces, as more witness reports arrive, as the trajectory solution tightens. The version of a fireball's parameters that goes viral on the first morning is almost never the version that ends up in the literature. That is normal science operating at news speed, and it is a completely different thing from being wrong on purpose. I want to be very clear about what I am and am not saying, because this is precisely the sort of thing that gets clipped and reposted with a caption about NASA lying. This is not evidence of concealment. Agencies do not conceal things by publishing two mutually contradictory numbers one paragraph apart on a public webpage that anybody can read. That is not what a cover-up looks like. That is what a rushed estimate looks like when the error bars get dropped for readability. But it is also true that the headline number everybody repeated and the headline object everybody pictured cannot both be right as stated. 10 tons of TNT and a 16-inch 170-pound rock are not compatible descriptions of the same event. At least one of them is off, probably substantially, and the honest position is that we do not currently know which, and this is exactly why the direction matters so much. Look at what just happened. The mass is uncertain by a factor of 5. The diameter inherits that uncertainty and adds its own. The energy is a modelled conversion of an optical measurement. Every single quantity that tells you what this object was is soft, but the direction does not depend on any of it. The direction comes from geometry. It comes from where the light started and where the light ended, measured against the ground, at a known time. It does not care what the rock was made of. It does not care how much it weighed. It does not care what fraction of its energy came out as visible light. You could be wrong about the mass by a factor of 100, and the object would still have been travelling due north. In a dataset where almost everything is an estimate wrapped in an assumption, the heading is the one clean thing we have. Which means that if we are going to answer the question in the title of this video, if we are going to say anything at all about where this rock came from, the direction is not just the best evidence available. It is very close to the only evidence available. Part 5. 5 volcanoes heard it. There is a detail in this story that I keep coming back to, and it is not the fireball at all. The airburst was recorded by instruments that were installed to listen for volcanic eruptions. The United States Geological Survey maintains infrasound equipment at volcanoes across the Cascade Range, and on the morning of the 14th of August, 5 of those installations picked up the pressure wave from a rock exploding 28 miles above a wheat field. Glacier Peak, Mount Rainier, Mount Adams, Mount St. Helens, Mount Hood. 5 volcanoes spread across 2 states and something like 400 miles of mountain range, all of them independently registering the same event. The arrival times are what make it obvious what happened. The flash was at 48 minutes past midnight. The signals came in between 55 minutes past midnight and 10 minutes past 1 Pacific time. So the earliest station heard it about 7 minutes after the light, and the last one heard it about 22 minutes after. That spread is not a mystery. It is a stopwatch. Sound travels through the lower atmosphere at roughly 0.34 kilometers per second. Multiply that by 7 minutes, and you get about 140 kilometers. Multiply it by 22 minutes, and you get about 440. Those are near enough the distances from Sims Corner to the nearest and furthest of those 5 volcanoes. The delays are exactly what you would predict if a single sound source went off over central Washington and the wave rolled outward across the state at the speed of sound, which is the point. Nobody had to decide that this was a meteor. The physics announced itself. Infrasound, if you have not run into the term, is sound below the range of human hearing, below about 20 Hz. The reason it is useful is that low-frequency sound loses energy very slowly as it travels, so where an ordinary noise dissipates within a few miles, infrasound can cross continents. That property is why the technology exists in the form it does. The global infrasound network that monitors for clandestine nuclear tests was built on exactly this principle. A large explosion anywhere on Earth generates a long wavelength pressure wave that can be detected thousands of kilometers away. The reason low frequencies survive and high frequencies do not comes down to how the atmosphere absorbs sound. Air absorbs acoustic energy in a way that depends strongly on frequency, and the higher the frequency, the more aggressively it gets soaked up. A sharp crack which is made of high frequencies dies within a few miles. A long, slow pressure oscillation with a wavelength measured in hundreds of meters or more barely notices the air is there. This is the same reason you hear the bass from a car stereo 3 streets away and none of the melody, and it is the same reason distant thunder is a rumble rather than a snap. There is a second effect at work over these distances, and it explains part of the spread in those arrival times. The atmosphere is not acoustically uniform. Temperature and wind vary with altitude, and sound bends toward regions where it travels more slowly, which means that acoustic energy leaving a source near the top of the troposphere does not all travel in a straight line along the ground. Some of it refracts upward, travels through the stratosphere, and bends back down hundreds of kilometers away. So a single event can arrive at a distant station by more than one path, and the apparent travel time depends on which path won. That is why infrasound arrival times get quoted as a window rather than a single number, and it is why the 15-minute spread across those 5 volcanoes is a reasonable spread, and not a sign that anything odd happened. The signature itself is also distinctive, which is how the analysts sorted it out. A volcanic eruption produces a long, messy, sustained acoustic signal as gas and ash push out of a vent over minutes. A rockfall produces a noisy, ragged burst. An airburst high in the atmosphere produces something much cleaner. A short, sharp pressure pulse with a characteristic shape that acousticians call an N wave. A rapid rise followed by a rapid drop back through ambient pressure, and then a recovery. It is the same waveform you get from any supersonic object, from a fighter jet to a bullet, scaled up enormously. Once you have seen one, you do not confuse it with a mountain. Volcano observatories use it for a more specific job. An explosive eruption, a rockfall, a lahar coming down a valley, a jet of gas venting from a vent, all of these produce distinct acoustic signatures, and if you can hear them, you can characterize what a mountain is doing without sending anybody up it. The instruments at Rainier and St. Helens are there because those mountains are dangerous and because the people whose job it is to watch them want more than one way of knowing what is going on. They are not there to catch asteroids. And here is the detail that I think makes the whole thing land. On that same Friday morning, at 6 minutes past 11 Pacific time, the Cascades Volcano Observatory issued its routine weekly update. Every volcano in the Cascade Range of Oregon and Washington, it confirmed, remained at normal background activity levels. Read that alongside the fireball detections, and you see what the observatory actually had to do that morning. 5 of their stations lit up with a pressure wave in the small hours. They had to look at those signals, determine that they were not volcanic, determine what they actually were, and then issue a routine all clear on the same instruments a few hours later. They separated a rock from space out of a volcano monitoring data stream correctly on the same morning, and treated it as unremarkable enough not to make a fuss about. That is a small piece of quiet competence, and it deserves saying out loud. But it also exposes something. There is no dedicated national bolide infrasound network in the United States. There is no agency whose job is to acoustically monitor the sky for incoming rocks. What exists instead is a patchwork. The nuclear test monitoring arrays, a handful of research installations run out of universities, and volcano monitoring stations like the Cascade instruments. Every one of those systems was built and funded for a different purpose. Bolide detection is a side effect, which means the quality of the record depends almost entirely on geography. Consider the counterfactual. Take this exact event, the same rock, the same speed, the same energy, and move it 800 miles east. Put it over the Nebraska sand hills at 1 in the morning. What do you get? Far fewer witnesses, because far fewer people. No dense array of infrasound stations, because there are no volcanoes to monitor. Maybe a lightning mapper detection if the geometry is favourable. The reconstruction would be dramatically worse, and the trajectory, if you could get one at all, would carry much larger errors. The August 14th event is well documented not because it was special, but because it happened to explode inside a volcano observatory's listening range, over a region with cameras, on a night when a meteor shower already had people looking up. And that is precisely why we can even ask the question in this video's title. The reason we know which direction this rock was travelling, to within 1/3 of a degree, is that it detonated in one of the few places in North America where a lot of instruments happen to be paying attention. Part 6. A lightning detector, 3 cameras, and a web form. Let me read you the actual list of things NASA used to reconstruct this event. Eyewitness accounts filed on the American Meteor Society website, data from 3 publicly accessible cameras, and the geostationary lightning mappers on the GOOS satellites. That is the list. That is all of it. I want to sit on the word 3 for a moment. Not 30, not a network. 3 cameras, described in the official write-up as publicly accessible, which is a polite way of saying they were not part of any scientific instrument program. They were cameras that happened to be pointed at the sky and happened to be reachable by somebody at NASA on a Friday morning. The most sophisticated piece of the whole reconstruction is the one that was designed for a completely different job. The Geostationary Lightning Mapper is an instrument that flies on the GOES weather satellites, parked in geostationary orbit about 22,000 miles above the equator. Its purpose is to map lightning across the entire Western Hemisphere continuously, day and night, so that forecasters can watch storms intensify in real time. It stares at the Earth and looks for brief flashes of light. Specifically, it looks at a wavelength of 777.4 nanometers. That is a particular emission line of atomic oxygen, and lightning produces it strongly, which is why the instrument was tuned there in the first place. Here is the accident. A meteor tearing through the upper atmosphere at 33,000 miles an hour also produces a burst of light at 777.4 nanometers. For exactly the same reason, it is violently exciting atomic oxygen. So the lightning mapper sees fireballs it was never asked to, it cannot help it. The result is that a weather satellite's lightning detector is currently one of the most reliable bolide sensors operating over North America. It has full disk coverage, it runs continuously, it timestamps to the millisecond, and it does not care whether it is cloudy at ground level. For a large fraction of the fireballs catalogued over the Americas in recent years, the satellite that caught them was a satellite that was looking for thunderstorms. Then there is the human layer, and this is where the uncertainty enters. Witness triangulation works like this. Somebody fills in a form describing where in their sky the light started and where it ended, using landmarks or compass directions or the position of the moon. Each of those descriptions, combined with the observer's location, defines a plane in three-dimensional space, the plane containing the observer and the object's path. Get two such planes from two well-separated observers, and their intersection is a line, and that line is the trajectory. Get 250 of them and you can start doing statistics on where the best fit line actually sits. It is genuinely clever, and it is genuinely limited. The American Meteor Society's own published caveats on this method are worth knowing, because they are unusually candid. Witness-derived radiant solutions carry typical uncertainties of 10 to 20 degrees. The solutions assume a fixed start altitude of 80 kilometers, because you have to assume something. Solutions that come out degenerate, where the geometry does not constrain the answer, get thrown out entirely. 10 to 20 degrees is a large number when the question is which patch of sky something came from. The full moon is half a degree across. 20 degrees is 40 moons laid end to end. If your question is roughly which direction, that is fine. If your question is whether an object came from one specific region of the ecliptic rather than the region next to it, 10 to 20 degrees is the difference between an answer and a maybe. I'm flagging that now, deliberately, before we get to the part of this video where I make an argument that rests on a direction, because I want you holding the error bar the whole way through, rather than having it sprung on you at the end. There is one more instrument in this story, and it is the strangest of the lot. NASA's assessment notes that Doppler weather radar indicates some small meteorites may be on the ground in the area. Weather radar, the same system that tells you whether to bring an umbrella. The technique works because a strewn field of falling meteorites is, from the radar's point of view, a small cloud of dense objects descending through the atmosphere. It shows up as a compact non-meteorological return, appearing shortly after the airburst and drifting downward and downwind over successive scans. It looks nothing like precipitation, and to a trained eye it is unmistakable. Match it against the fragmentation point and you can localize the fall zone to within a few kilometers. This is not theoretical. It is the same method that was used in March of this year after a fireball over Houston, where NASA used Doppler radar to track the falling debris and narrow down where to look. To understand why it works, you have to understand what happens after the flash goes out, and it is a phase almost nobody thinks about. When a meteoroid fragments and its pieces slow, below roughly 3 kilometers per second, they stop glowing. The plasma sheath collapses, the light goes out, but the rocks are still there, and they are still 28 miles up, and now they simply fall. That phase is called dark flight, and it can last several minutes. During it, the fragments are no longer behaving like meteors at all. They are behaving like stones dropped from an aircraft. They decelerate to terminal velocity, which for a fist-sized meteorite is a few hundred kilometers per hour, and then they drift. because the upper-level winds are pushing them sideways the entire way down. A fragment falling from 45 kilometers through a stiff westerly can end up many kilometers from directly below the point where it stopped glowing. They also sort themselves by mass. Heavier fragments carry more momentum per unit of drag, so they penetrate further along the original direction of travel before the air wins. Lighter fragments stop sooner and get pushed further by the wind. The result is that a strewn field is not a circle. It is an elongated ellipse, with the small pieces at one end and the big ones at the other, oriented along the ground track. If you find one stone, you can usually predict where to walk to find the next. The radar sees all of this while it is happening, in the several minutes between the flash and the impacts, which is exactly the window in which nothing else is watching. So take a step back and look at the apparatus we have assembled here. A weather satellite's lightning detector, 3 cameras that happen to be pointed up, a few hundred members of the public filling in a web form, 5 seismic stations installed to listen for volcanoes, and a weather radar built to forecast rain. Not one item on that list was designed to do the job it did on the 14th of August. And out of that improvised, borrowed, entirely accidental collection of instruments came a trajectory precise enough that we can compute a heading to 1/3 of a degree. Every number in this story is an estimate produced by a machine built for something else. Every number except 1. So let us go and find out what that one number says. Part 7. The only evidence is a direction. You can work out where a meteor came from using nothing but where it started, where it ended, and what time it was. That sentence sounds like it should be more complicated than it is, so let me show you the whole thing, step by step, with the actual numbers. By the end of the next few minutes you will have done the calculation yourself, and you will understand exactly why the answer is interesting. The principle is simple. Over the last 100 or so kilometers of its journey, a meteoroid travels in a straight line. Gravity is bending its path, but over 4 seconds the bending is negligible, and the atmosphere is slowing it down, but slowing something down does not turn it. So the trajectory through the atmosphere is, for practical purposes, a straight segment of the line the object was already travelling on before it arrived. Extend that segment backwards, out past the top of the atmosphere and into space, and you're pointing at where it came from. That backward extension, projected onto the sky, is the radiant. Step 1. The ground track. Start point, 47.412 degrees north, 119.412 degrees west. End point, 47.850 degrees north, 119.408 degrees west. The change in latitude is 0.438 degrees. The change in longitude is 0.004 degrees, and at this latitude a degree of longitude is shorter than a degree of latitude, so that tiny east-west component shrinks further still. Run the arctangent and the heading comes out at 0.35 degrees. Due north is 0. This object was travelling north to within 1/3 of a degree. Step 2. The entry angle. It lost 32.4 kilometers of altitude while covering 48.7 kilometers of ground. The angle whose tangent is 32.4 over 48.7 is 33.6 degrees. So the object came in at a slant of about 34 degrees below the horizontal, climbing backwards along that line into space. Step 3. What the sky looked like at that instant. This is the part that requires a little care because the sky moves. The Earth turns once every 23 hours and 56 minutes, so the patch of sky sitting above any given point on the ground changes continuously. To know which direction in space corresponds to a given direction in the local sky, you need the local sidereal time, which is astronomers' language for how far the Earth has rotated relative to the stars rather than relative to the Sun. For the entry point above Soap Lake, at 07 hours, 48 minutes, 33 seconds, Coordinated Universal Time on the 14th of August 2026, the local sidereal time works out to 21.37 hours. Step 4, where the Sun was. On that date the Sun sat at a right ascension of 9.60 hours and a declination of plus 14.32 degrees. Right ascension and declination are just longitude and latitude projected onto the sky. Nothing more complicated than that. Step 5, the anti-solar point. Directly opposite the Sun, on the far side of the sky, is a point astronomers call the anti-solar point. It is always exactly 180 degrees from the Sun, which means at local midnight it is high overhead, and its position is trivially computed from the sun's. Add 12 hours to the right ascension and flip the sign of the declination. So on the 14th of August 2026, the anti-solar point was at right ascension 21.60 hours, declination minus 14.32 degrees. Step 6. Convert that to the local sky over Washington. Given a local sidereal time of 21.37 hours and a latitude of 47.4 degrees north, the anti-solar point sat at an altitude of 28.2 degrees above the horizon, at an azimuth of 176.2 degrees. Now stop and read the azimuth again. 180 degrees is due south. 176.2 degrees is south, within 4 degrees. At the exact moment this fireball appeared over central Washington, the anti-solar point was hanging almost precisely due south, about 28 degrees above the horizon, roughly a third of the way up the southern sky. And an object that appears to come from a point due south travels north, which is what this object did, to within a third of a degree. There is one refinement a professional would insist on here, and it is worth understanding because it makes the result stronger rather than weaker. The direction a meteor appears to come from is not quite the direction it was travelling before it met Earth. Our planet's gravity has been pulling on the object for the whole of its final approach, bending its path inward and speeding it up. So the apparent radiant, the one you get by extending the atmospheric track backwards, is pulled slightly toward the point directly overhead compared to where the true radiant sits. Meteor astronomers call this zenith attraction, and correcting for it is standard practice. The size of that correction depends on speed. For a fast meteor arriving at 60 kilometers per second, Earth's gravity is a minor perturbation on an already enormous velocity, and the shift is small. For a slow meteor arriving at 14 or 15 kilometers per second, the correction is much larger, because the 11.2 kilometers per second that Earth's gravity contributed is a substantial fraction of the total, which means that for our object specifically, the true pre-encounter direction sat further from the overhead point than the apparent one did. The apparent radiant was already low, at 28 degrees. Correcting for zenith attraction pushes the true radiant lower still, closer to the horizon, closer to the ecliptic. It moves the answer further into the region we're about to talk about, not out of it. Let me put the two candidates side by side one last time, because the contrast is the entire argument. The Perseid radiant at that same instant, from that same spot, altitude 39.7 degrees, azimuth 43.5 degrees, northeast, high. A meteor from there crosses the sky toward the southwest. The anti-solar point, at that same instant, from that same spot, altitude 28.2 degrees, azimuth 176.2 degrees, due south, lower. A meteor from there crosses the sky toward the north. The observed motion was north. One of those candidates matches the observation. The other one is close to the reverse of it. This is not a marginal call, and it does not require you to trust anybody, including me. It requires a calculator and about 20 minutes. Now, before I tell you why the anti-solar direction is interesting, I need to lay out the caveats, and I am going to do it now rather than after the payoff, because a caveat that arrives after the reveal is an excuse, and a caveat that arrives before it is an argument. First caveat. Everything I just computed is derived from NASA's published start and end coordinates. It is not a published radiant solution. NASA gave a trajectory. I turned that trajectory into a direction on the sky. Those are different objects, and I want you to know which one you're looking at. Second caveat. As we covered a moment ago, witness-derived trajectory solutions carry typical radiant uncertainties of 10 to 20 degrees. The gap between the Perseid radiant and the anti-solar point in this case is well over 100 degrees, so the Perseid exclusion survives that error bar comfortably, but the positive identification does not survive it as cleanly, and I will come back to exactly what that costs us. There is a related point buried in that second caveat which is worth pulling out, because it is the thing that decides how much weight this whole argument can carry. The 10 to 20 degree figure is the uncertainty on a radiant derived from witness reports alone. This event had more than that. It had the satellite lightning mapper, which timestamps the flash precisely and locates it geographically. It had 3 cameras, and it had a couple of hundred witness accounts to constrain the solution rather than define it. A trajectory assembled that way is better than a purely witness-derived one. though how much better is not something the published assessment quantifies. So the honest range on this particular radiant is somewhere between very good and merely acceptable, and nobody outside the office that computed it can currently say which. Third caveat, and this is the big one. The region of sky around the anti-solar point is not a small target. It is broad. Rocks arrive from it constantly on every night of the year, so saying that an object came from that general direction is not the same as saying it came from something specific. It is a probability statement, not an identification. And fourth, one event is one event. A single fireball, however well measured, does not establish anything on its own. It is a data point. What matters is what it is a data point in. With all of that on the table, here is the thing. The anti-solar direction has a name in meteor astronomy. It has had that name for a very long time, and until this year almost nobody outside the field had any reason to care about it. This year, that name got attached to a number that nobody has been able to explain. Part 8. The Antihelion Source. It is called the Antihelion Source. The first thing to get straight is what it is not, because the name sounds like a meteor shower, and the instinct is to file it next to the Perseids and the Geminids. That instinct will lead you wrong. The Antihelion Source is not a shower. It has no parent comet. It has no peak night. It does not have a date on the calendar. It does not have a predicted rate, and there is no year in which it is stronger or weaker in the way a shower can be. It is a broad, permanently active, diffuse region of sky, centered roughly opposite the sun, lying close to the plane of the ecliptic. It is on tonight. It was on last night. It will be on in February. If you have never heard of it, that is exactly why. There is nothing to announce. Nobody writes an article telling you to go outside and watch the Antihelion Source, because it produces a handful of meteors an hour at best, spread out over a wide patch of sky, every single night, forever. It also has a twin that almost nobody ever sees. Directly opposite the Antihelion Source, on the sunward side of the sky, sits the Helion Source, produced by the same kind of bodies approaching from the other side of Earth's orbit. It is just as active. We almost never observe it, for the most obvious reason imaginable. It is behind the sun, and you cannot look at a meteor radiant in daylight. Radar can, and radar shows it is there. But visually the Helion Source is invisible, which means half of this entire population has been effectively hidden from human eyes for the whole history of the subject. There is also a piece of history here that explains why the name sounds unfamiliar even to people who follow meteor showers. For most of the 20th century, the activity along this stretch of the ecliptic was catalogued as a long list of separate, faint, individually named minor showers, each supposedly with its own radiant and its own dates. Over time, it became clear that those distinctions were largely artificial. The radiant does not jump from one shower to another. It drifts smoothly along the ecliptic, roughly a degree a day, tracking the anti-solar point as Earth moves around the sun. The modern treatment abandoned the list of names and replaced it with a single continuous source, which is what we now call the Antihelion Source. A whole page of the old catalogue collapsed into one entry. That drift, by the way, is why the calculation we did in the last part had to be done for a specific moment. The Antihelion radiant on the 14th of August is not where it was on the 1st of August, and it is nowhere near where it was in March. You cannot look this up in a table. You have to compute where the sun was, and then look at the opposite side of the sky, which is exactly what we did. So what is actually generating it? The population behind the Antihelion Source is a set of bodies on orbits with three shared properties. They are prograde, meaning they go around the sun in the same direction as the planets rather than backwards. They are low inclination, meaning they lie close to the plane the planets orbit in rather than cutting across it at a steep angle, and their semi-major axes sit near one astronomical unit, meaning they go around the sun on roughly the same sort of timescale Earth does. Put all three together and you get objects that are, in orbital terms, Earth's neighbours. They are moving in the same direction, in the same plane, at similar distances. Now think about the encounter geometry that produces. If a rock is moving the same way you are, at a similar speed, you do not slam into it head-on. You catch up to it, or it catches up to you. It is the difference between two cars colliding at a crossroads and one car rear-ending another on a motorway. The relative speed is far lower, even though both objects are individually moving very fast. That is why antihelion entry speeds are low, typically somewhere in the range of 15 to 30 kilometers per second, against 59 for a Perseid and 70 plus for the fastest showers, And here is where the physics starts paying out consequences. Kinetic energy scales with the square of speed. An object arriving at 15 kilometers per second carries roughly 1/16 the energy per kilogram of an object arriving at 60. That changes everything about what happens to it in the atmosphere. Less energy per kilogram means less violent ablation. Less violent ablation means the object survives longer. Surviving longer means it penetrates to lower altitudes, into thicker air, where its shock wave has a real chance of reaching the ground. And penetrating to lower altitudes before it fails means that when it does fail, the surviving fragments have less distance to fall and less time to be destroyed, which is to say, slow rocks make it further down, make more noise, and are far more likely to leave something behind. Now look at what happened over Washington on the 14th of August. The object penetrated to 45.5 kilometers. It produced a shock wave that arrived at the ground with enough energy to be heard in Spokane and to register on 5 volcano monitoring stations, and it left a radar signature suggesting that pieces of it are lying somewhere in Douglas County right now. That is not a fast meteor's behavior. That is exactly, point for point, how a slow one behaves. So we have 4 independent lines of evidence, and they all point in the same direction. The direction itself, due north, meaning a radiant due south, which is where the anti-solar point was. The speed, 14.6 kilometers per second, sitting right at the low end of the Antihelion range and nowhere near any shower. The entry angle, 33.6 degrees, a shallow to moderate slant, which is characteristic of the Antihelion population precisely because those objects are being overtaken rather than met head-on. And the survival behavior, deep penetration, ground-level sound, probable meteorites. 4 different measurements, from 4 different physical arguments, and none of them contradicts the others. It is worth pausing on how much of a coincidence that is not. These 4 measurements are not 4 ways of saying the same thing. The direction comes from geometry on the ground. The speed comes from the trajectory solution. The entry angle comes from the ratio of altitude lost to distance covered. The survival behavior comes from acoustics and radar. 4 separate physical arguments, drawing on 4 separate instruments, none of which knows what the others concluded. When independent lines converge like that, it is usually because they are converging on something true. And the reason they converge is that all 4 are downstream of the same underlying fact, the orbit. If a rock is on a low inclination, prograde, roughly 1 astronomical unit orbit, then it must approach Earth from near the antisolar direction. It must arrive slowly, it must enter at a shallow angle, and it must therefore penetrate further. Those are not 4 properties, they are 1 property, observed 4 ways. Where did these bodies come from originally? Almost certainly the main asteroid belt. The belt is not a static place. Gravitational resonances with Jupiter carve gaps in it, and material that drifts into one of those gaps has its orbit stretched and pumped over hundreds of thousands of years until it crosses the orbits of the inner planets. This has been happening continuously for 4.5 billion years. It is the single most ordinary delivery mechanism in the solar system, and it is the reason there is a steady population of rocks on Earth crossing orbits at all. And that ordinariness is the honest conclusion here, so let me say it before anyone accuses me of hiding it. Identifying an object as Antihelion source does not make it strange. It makes it typical. Antihelion rocks arrive constantly. On any given night, a decent fraction of the sporadic meteors over your head are coming from that general region. If all we had established was that a fireball over Washington came from the anti-solar direction, the correct response would be a shrug and an early night. Nothing about a single Antihelion fireball is remarkable, unless somebody has already gone and measured how many of them have been arriving this year. Part 9. 14 against 3. Point 6. In the first 3 months of 2026, somebody did exactly that. The American Meteor Society took every fireball from the quarter for which a trajectory could actually be solved, which came to 67 events, and computed a radiant for each one. Then they compared where those 67 radiants fell against the baseline distribution from the 5 previous years, 2021 through 2025. They were not fishing. The reason they ran the analysis in the first place is that the report counts had gone strange, and the obvious question when counts go strange is whether the extra events are coming from anywhere in particular. The tight Antihelion zone should have produced about 3.6 events in that quarter. That is what 5 years of baseline says, It produced 14. In statistical terms, that is a 4.1 sigma result. If you have not spent time around that language, here is the plain version. It means that if nothing unusual were happening and you ran that same quarter over and over, you would expect to see a pileup that large roughly once in every 40,000 attempts. The density figure makes it more concrete, 9.6 events per 1,000 square degrees of sky, concentrated in that zone. That is double the previous maximum ever recorded there in the baseline period, and the population statement is the one I find hardest to look away from. Of the 67 trajectory resolved fireballs in that quarter, 22 of them tracked the anti-solar point across the sky, on low inclination prograde orbits near 1 astronomical unit, with shallow entry angles. 22 out of 67. Textbook Antihelion geometry, at something like 3 to 4 times the normal rate. Now hold that against the object we have been discussing for the last hour. Due north track, meaning a southern radiant sitting where the anti-solar point was. 14.6 kilometers per second, low. 33.6 degree entry, shallow. Low inclination, prograde, roughly 1 astronomical unit, all implied by that speed. It is the same description. Word for word, it is the description of the 22. Now, a fair objection, and one you should always raise when somebody waves a sigma value at you. If you slice the sky into enough regions and test every one of them, some of those tests will come back looking significant by chance alone. That is the multiple comparisons problem, and it is the graveyard of a great many exciting results. So the honest question is not whether 4.1 sigma sounds impressive, it is whether the zone was chosen before the data was looked at or after. In this case, the Antihelion zone is not an arbitrary patch. It is a pre-existing, named, physically motivated region of sky that meteor astronomers have been tracking for decades, with a 5-year baseline computed for it in advance. It was not drawn around the events after the fact. That does not make the result bulletproof, but it does mean this particular objection has less purchase than usual. There was a second cluster in that same analysis, and it is stranger still, though it is not the one this video is chasing. 12 events came from radiants above 70 degrees declination, which is to say from very close to the northern celestial pole. The expectation was 2.4. That is a 4.3 sigma result, roughly 1 in 118,000, against a previous single-year maximum of 5, set in 2021. 2 separate independent concentrations in 2 completely different parts of the sky, in the same quarter, both at better than 4 sigma. And the events themselves are not statistical abstractions. They have names and dates and, in a couple of cases, physical remains. On the 8th of March, a daylight bolide crossed Western Europe and drew 3,229 reports from France, Germany, Switzerland, Belgium, and the Netherlands, with an average reported duration of 5.5 seconds and 174 accounts of delayed sound. Fragments were recovered, and the suspected classification was diogenite. 9 days later, on the 17th of March, a roughly 2-metre, 7-ton object came in over Lake Erie at 57 minutes past 8 in the morning, in full daylight, released about 250 tons of TNT, and was seen from 16 states and Ontario. 222 reports. A Eucrit was recovered and confirmed, and its radiance sat at a declination of plus 77 degrees, which puts that event squarely inside the second, high declination cluster. 4 days after that, on the 21st of March, a roughly 1-ton object broke apart 29 miles above Houston at 20 minutes to 5 in the afternoon, releasing about 26 tons of TNT, and put a fragment through somebody's roof in a neighborhood called Ponderosa Forest. Preliminary classification, an ordinary chondrite. 3 recovered falls inside about 10 days. The worldwide baseline is roughly 10 recoveries in an entire year. As Mike Hankey of the American Meteor Society put it to Space.com at the time, we might see 10 meteorite recoveries a year worldwide, and we had 3 recoveries in 10 days. That is the part of the 2026 anomaly that has never been touched by any statistical argument, because it is not a statistic. It is rocks in boxes. And the quarter boundary did not turn it off. The American Meteor Society's Fireball log recorded 4,462 entries in April alone, against 2,567 in January and 2,280 in April of 2025. On the 15th of June, at around 26 minutes past 3 Coordinated Universal Time, a single event drew 556 reports across 18 states, which is larger on witness count than any North American event of the first quarter surge. Whatever was happening, it did not politely stop at the end of March because a quarter had ended. We covered this analysis at the end of March when it was published, so I'm not going to rebuild it from scratch here. What I want to do instead is be scrupulously fair about the other half of it, because the count side of the same document is much weaker than the radiant side, and the honest version of this story requires admitting that. The counts went like this: 2,322 total fireball events logged in the quarter, which is the highest figure on record but only marginally above 2022's 2,168 and 2021's 2,065. 70 events drew 25 or more independent reports, against a baseline around 43. 40 events drew 50 or more reports, against a baseline around 20, which is a doubling and a 3.9 sigma departure. 16 events drew 100 or more, against a baseline of about 8. Those are real numbers, and they look dramatic. But the American Meteor Society itself pointed out the problem with them, which is a thing I always want to give an organization credit for doing. Fireball counts are overdispersed. The variance to mean ratio in that dataset is 46.5, which means the year-to-year scatter is enormous compared to what a simple Poisson process would produce. If you handle that properly by using a negative binomial model instead, the excess in the total count comes out at 1.8 sigma, which is not significant, which is nothing. They said so themselves in their own analysis about their own headline number, so the anomaly was never really about how many rocks arrived. That part was always shaky and its authors knew it. What was solid was where they came from, and what they did on the way down. Sonic booms reported on 82.5% of the largest events, and 3 separate meteorite recoveries inside about 10 days, against a worldwide baseline of roughly 10 recoveries in an entire year. Direction and physical residue. Those were the 2 legs the anomaly actually stood on. And then in July, a paper arrived that a great many people took as settling the whole thing. Part 10. The null result that counted the wrong thing. The paper is by Althea V. Moorhead of NASA's Meteoroid Environment Office, and it has one of the better titles in recent astronomy. A cornucopia of null results, a statistical analysis of fireballs reported to the American Meteor Society. It was submitted on the 6th of July 2026 and announced in the EMET Meteor Journal 2 days later. What it does is apply Poisson regression to American Meteor Society fireball counts. The paper doubles as a teaching document, walking through the technique in enough detail that another researcher could replicate it, which is a genuinely good thing to put into the world, and I want to say so plainly. What it finds is that the number of events reported in early 2026 is in line with the overall pattern of activity, and that there is little evidence for the so-called February fireballs phenomenon. That is a null result, and it is a real one. I'm not about to tell you it is wrong. It is competent work from the right institution by somebody who does this for a living, and the finding stands. But I want you to notice, very carefully, what it is a null result about. Counts, numbers of events per unit time, how many fireballs got reported, and whether that number in early 2026 departs from the trend once you model the trend properly, rather than testing against a flat line. That is the entire scope. It is not a null result about radiance. It contains no analysis of where in the sky the fireballs came from, because that is not what a count regression does. A model that describes how many events arrive per month has no mathematical machinery for explaining why 22 out of 67 trajectory-resolved events tracked one narrow band of ecliptic sky. Those are different questions, asked of different data, requiring different methods. It is worth understanding why 2 competent analyses of the same public data can come out looking like they disagree, because the answer is not that one of them made a mistake. It is that they ask slightly different questions. The American Meteor Society's approach was to take the 5 years before 2026, compute an average rate, treat that as a flat expectation, and ask how unlikely 2026 looks against it. That is a perfectly standard test, and against a flat baseline the early 2026 numbers look extreme. Poisson regression does something different. Instead of assuming the baseline is flat, it fits a trend through the whole time series, allowing the underlying rate to grow year over year, and then asks whether any individual year departs from that fitted trend. And here is the subtlety. 2026 is one of the years the trend is fitted to. A high value at the end of a series pulls the fitted trend line upward toward itself and then gets compared against the line it just helped raise. This is not a flaw in the method. It is what the method is for, if you believe the underlying rate genuinely has been climbing. But it does mean that a regression will always be more forgiving of a final year excess than a flat baseline test will be. Which of those two framings is right depends entirely on whether you think fireball reporting rates have a real upward trend. And they almost certainly do, for reasons that have nothing to do with the sky. There are more people with smartphones every year. There are more dash cams and doorbell cameras every year. There are more ways to find a reporting form. If the reporting rate is climbing for purely terrestrial reasons, then modelling the trend is the correct move and the null result is the right answer. But notice what that argument can and cannot do. Better reporting can absolutely inflate how many fireballs get logged. It cannot manufacture a sonic boom. It cannot put a meteorite in a field. And it cannot make rocks arrive preferentially from one part of the sky. Because the number of people holding phones has no opinion about the ecliptic. And there is an awkwardness in the overlap that I think got missed almost universally in the coverage. The metric the null result landed on is precisely the metric the American Meteor Society had already conceded was not significant. Remember the negative binomial, 1.8 sigma on the totals, by their own admission, in their own document months earlier. So we ended up with two competent Poisson treatments of the same public data appearing to disagree, when in fact one was testing against a flat baseline and the other was modelling the underlying trend, and the substantive conclusion of both is that the total count is not the interesting part. Which is correct. The total count was never the interesting part. We went through all of this in our video from the 1st of August, when we asked what was really falling out of the sky earlier this year, so I will not relitigate it. The short version is that the counts got resolved, the physical residue did not, and the directions were never touched by anybody. I also want to name the reason this matters beyond meteor astronomy, because it is a pattern you will recognise from every field where a strange result meets a headline. A question got asked, is something unusual happening in the near-Earth environment? That question had two independent components, counts and directions. One of those components was easier to test because count data is abundant and the statistical tools are off the shelf. The other required trajectory solutions which exist for only a fraction of events and take real work to produce. So the easy half got tested, the test came back negative, and the story became that the anomaly had been debunked. Nobody lied. Nobody even overclaimed particularly. The paper says exactly what it did and no more. But a null result on the tractable half of a question has a way of being reported as a null result on the whole question, and once that has happened, the untested half stops getting attention entirely. It is not a conspiracy. It is just how attention works. So here is where that leaves us, and this is the point the whole video has been walking toward. Strip away everything that was argued about and explained away. What remains standing, unexplained, from the strangest year the American Meteor Society has on record, is a direction. A 4.1 sigma concentration of large fireballs arriving from one narrow region of ecliptic sky, with a second, separate 4.3 sigma concentration near the North Celestial Pole, and not one published analysis has addressed either of them. And in the small hours of the 14th of August, over a wheat field in Douglas County, Washington, something came out of approximately that direction, at approximately that speed, at approximately that entry angle, and exploded with the force of 10 tons of TNT. One event proves nothing. I have said that twice, and I will say it again before the end. But you have to admit it is an interesting place for a rock to fall out of. Part 11. The Answers That Are Wrong. An unexplained light over a defense-heavy stretch of the American West at 1 in the morning generates confident explanations within about 90 minutes. I'm not being sarcastic about that. It is a completely human response, and some of the explanations people reached for are the kind of thing a reasonable person would think of. The reason to work through them carefully is not to score points. It is that each wrong answer eliminates a possibility, and by the time you've eliminated all of them, you have a much sharper picture of what the right answer has to look like. Start with the most plausible of the wrong answers, that this was a re-entering satellite or rocket body. It is a good guess. There is a great deal of hardware in low Earth orbit. Pieces of it come down regularly, and a re-entry does produce a spectacular fireball with fragmentation and sonic booms. If you saw the footage with no other information, Re-entry would be a sensible first thought. The speed kills it. Objects in low Earth orbit travel at roughly 7 to 8 kilometers per second, because that is what orbital velocity is at that altitude. It is not a range you can push. If you're going faster than about 8 kilometers per second near Earth, you're not in a circular orbit. You're on your way somewhere. This object was measured at 14.6 kilometers per second, roughly double orbital speed, and there is no configuration of orbital debris that arrives at double orbital speed. Only something on a heliocentric orbit, something that was going around the Sun rather than around the Earth, arrives that fast. The behavior kills it too, independently. Re-entering hardware is a large, structurally complex low-density object, and it comes apart progressively. What you see is a long, slow, multi-object train, pieces separating and trailing and glowing at different colours, visible for tens of seconds and frequently over a minute. It is unmistakable once you have seen one. This was a single object. 4 seconds of luminous flight, 1 terminal fragmentation, a shock wave, and a radar debris signature. Nothing about that profile resembles a re-entry. Second wrong answer, a missile test, or some classified vehicle. The problem here is the witness list. This event was recorded by satellite lightning mappers looking down from geostationary orbit, by publicly accessible cameras on the ground, by several hundred civilian observers across 2 sovereign countries, and by 5 United States Geological Survey infrasound stations, whose data goes into a public monitoring program. It produced a natural bolide acoustic signature at 45 kilometers altitude on a ballistic path. There is no plausible test corridor that runs due north over Douglas County, Washington, at 33,000 miles an hour, at 1 in the morning, terminating in an airburst 28 miles up. And if there were, running it directly over a volcano observatory's acoustic array would be a remarkable choice. Third, that somebody knew it was coming, and did not warn anyone. Robert Lunsford answered this one himself on the record, and I quoted him earlier. "Fireballs are always a surprise. They have to be extremely large to be visible before they enter the atmosphere. The American Meteor Society had no idea this was coming, and neither did anybody else. The arithmetic behind that is worth spelling out. Planetary defense surveys are designed and funded to find objects 140 meters across and larger, because that is the size at which an impact becomes a regional catastrophe. Even at that size, the job is nowhere near finished. As of February of this year, NASA's Planetary Defense Coordination Office put the catalogued fraction at roughly 40%, with something on the order of 15,000 objects at 140 meters and above still undiscovered. Our object was about 0.41 meters across. That is roughly 340 times smaller than the smallest thing the surveys are built to find, which means it is not merely undetected, it is beyond the reach of the instruments entirely. There is no telescope on Earth or in orbit that could have picked up a dark, cold 16-inch rock at any useful distance. This is an aperture story. It is not a secrecy story. Those are very different failures, and only one of them is anybody's fault. Fourth, that this is debris from the interstellar object that generated so much speculation earlier this year. That idea circulated widely during the spring surge, and it fails on 2 independent grounds. Geometrically, a single hyperbolic source arriving from one direction in interstellar space produces one tight radiant, because everything in the stream is on essentially the same trajectory. The observed 2026 pattern was a broad Antihelion concentration, plus a completely separate high declination cluster near the north celestial pole. One source cannot produce 2 widely separated radiants, and mineralogically, the recovered stones from the spring were inner solar system material from a differentiated parent body, which is not what interstellar debris would look like. That case was closed out on this channel 2 weeks ago, and it has not reopened. Which leaves the most interesting wrong answer, and the one I want to treat with the most care, that something is being deliberately sent at us from one direction. The underlying observation there is real. There is a 4.1 sigma directional excess and nobody has explained it. I have spent most of this video saying so. But look at which direction it is. The Antihelion source corresponds to prograde, low inclination orbits near 1 astronomical unit, which is the most crowded, most ordinary, most thoroughly expected orbital neighbourhood in the entire inner solar system. If you wanted to pick a direction from which an intelligently directed object would arrive, you would not pick the one that is already full of naturally occurring traffic. You would notice something arriving from somewhere nothing normally comes from. The word doing all the work in that theory is unexplained, and unexplained means unexplained. It does not mean directed. And there is a perfectly natural explanation available that would be genuinely exciting if it turned out to be right. If a modest-sized asteroid broke up in the relatively recent past, on a low-inclination orbit near Earth's, the fragments would spread along that orbit into a stream. Earth crossing that stream would produce exactly what was measured, an elevated rate of large, slow asteroidal fireballs from one narrow band of ecliptic sky, persisting for a period and then fading as we pass through it. That would be new science. It would also be entirely unremarkably natural, and it is the sort of thing you would only ever detect by paying attention to directions. Part 12. Nobody could have warned you. Nobody saw it coming. I want to spend a few minutes on why, because the reason is more interesting than the fact. A 16-inch rock in space is, for all practical purposes, invisible. It is dark because most asteroidal material reflects only a few % of the light that hits it. It is cold, so it does not radiate meaningfully in the infrared at the distances that matter. It is small enough that even at the distance of the Moon, it would be far below the detection threshold of any survey telescope operating today. And it is moving, so it would not sit still in an image long enough to be built up over multiple exposures. The only moment at which an object like this becomes detectable is the moment it becomes luminous. And it becomes luminous by hitting the atmosphere. By then, the question of a warning is academic. This is what Lunsford meant by that line about fireballs having to be extremely large to be visible before they arrive. Pre-impact detections do happen. There have been a handful of cases where an incoming asteroid was spotted hours before entry, and the impact point was predicted correctly. Every one of them involved an object several meters across, and every one of them was treated as a triumph, precisely because it is so hard. Several meters is more than 10 times the size of our object, and volume scales as the cube of size, so 10 times the diameter is 1,000 times the mass. The gap between what we can catch and what came down over Washington is not marginal. It is enormous. It is worth asking why the surveys draw their line at 140 meters, because the number is not arbitrary, and it explains the whole shape of the problem. Impact energy scales with mass, and mass scales with the cube of diameter. Double the size of an object and you get 8 times the energy. That cubic relationship means the damage curve is brutally steep. A rock a few meters across produces an airburst that breaks windows. A rock tens of meters across can flatten a forest. Somewhere in the low hundreds of meters you cross into the range where an ocean impact generates a serious tsunami, and a land impact destroys a region rather than a town. 140 meters is roughly where the consequences stop being local and start being national, which is why that is the threshold written into the survey's mandates. The corollary nobody likes is that everything below the threshold is deliberately out of scope, not overlooked, not underfunded, out of scope by design, because a survey that tried to catalogue everything down to a meter would need instruments that do not exist and would still miss most of it, and the detection physics gets worse as objects get smaller, faster than you would expect. Brightness falls off with the square of size and with the 4th power of distance for a sunlit object seen from Earth. That 4th power is what does the damage. Halve the size and you have quartered the brightness. Double the distance and you have cut it by 16. A 140-meter asteroid is detectable out to tens of millions of kilometers, which buys you years of warning. A 4-meter one is detectable at roughly lunar distance if you are lucky, and it is coming from the right part of the sky, which buys you hours. A 16-inch one is not detectable at any distance that matters at all, so let us look at what that gap actually contains, using this channel's own year of coverage as the ruler. In March, over Lake Erie, an object roughly 2 meters across and weighing about 7 tons came in during daylight and released about 250 tons of TNT. It was seen from 16 states and Ontario. A meteorite was recovered and confirmed as a Eucrate. 4 days later, over Houston, an object weighing about 1 ton broke up 29 miles above the city at 20 minutes to 5 in the afternoon, released about 26 tons of TNT, and put a fragment through the roof of a house. And on the 14th of August, over Douglas County, an object weighing about 170 pounds as published released about 10 tons of TNT 28 miles up, was seen across 4 jurisdictions and rang 5 volcano stations. Line those 3 up and you have a ladder. 7 tons, 1 ton, and something under 1/10 of a ton. 250 tons of TNT, 26 tons and 10. The August event is an order of magnitude below the Houston event on both mass and energy, and roughly 2 orders of magnitude below the Lake Erie one, and it still woke people up across 3 states and a province. That is the point of the ladder. The class of event that is visible, audible, window rattling, and capable of dropping rocks on your neighbourhood starts far, far below anything any survey is designed to see. The surveys are looking for the events that would end a city. They are not looking, and are not built to look, for the ones that merely terrify a region. Which brings us back to the improvised instrument problem, and I want to frame this as a consequence rather than a complaint. Everything we know about the August 14th event came from apparatus funded for other missions. The Lightning Mapper was funded to improve storm forecasting. The volcano infrasound was funded to keep people from being killed by Mount Rainier. The weather radar was funded to tell you whether to cancel a picnic. The cameras were funded by whoever owned the buildings, and the witness reports were funded by nothing at all, by a few hundred people choosing to fill in a form for free at 2 a.m. That system works surprisingly well. It produced a trajectory good enough for us to compute a heading to 1/3 of a degree, which is genuinely impressive given what it was built out of. But it is entirely dependent on those other missions continuing to exist, and it produces exactly the error bars you would expect from borrowed tools. The American Meteor Society has been asking for years for a national all-sky camera network. Not a research curiosity, a dedicated grid of cameras running continuously, covering the country, purpose-built for this. Here is what that would change. With 2 or more dedicated cameras seeing the same event from known positions with precise timing, you do not triangulate impressions, you measure the path directly. The trajectory comes out with errors of fractions of a degree instead of 10 to 20. And once the trajectory is that good, you can integrate the orbit backwards and say, with real confidence rather than reasonable inference, exactly which orbit the object was on before it arrived. Which is to say, if that network existed, the question this entire video is built around would not be an argument. It would be a number. Somebody would simply look up the pre-atmospheric orbit of event 6582, compare it to the Antihelion population, and tell you yes or no in about 4 seconds. The reason we are reasoning instead of reading is that nobody funded the cameras. Part 13. The rocks on the ground. There is one thing that could settle all of this, and it is currently lying in a field somewhere in Douglas County. NASA's assessment includes a sentence that meteorite hunters across the Pacific Northwest read the way other people read a lottery result. Doppler weather radar indicates that some small meteorites may be on the ground in the area. We covered how the radar detection works earlier. What I want to do now is talk about what would happen if somebody actually finds one, because a recovered stone answers questions that no amount of statistical argument can touch. First, where to look. Lunsford, speaking before the full trajectory solution was public, guessed that fragments might come down near Bridgeport or Brewster, 2 small towns on the Columbia River in the northern part of the county. NASA's own fragmentation point sits above Sims Corner, some distance to the south. Those are different guesses, and the difference between them is exactly the dark flight problem. The fireball stopped glowing in one place, and the rocks landed somewhere downrange and downwind of it, and how far depends on the wind profile that night and the mass of each fragment. What works in everybody's favour here is the terrain. This is the channeled scablands, shrub steppe, basalt, dryland wheat, very little tree cover, very little standing water, very few buildings. A dark stone sitting on pale soil or stubble is genuinely findable. Compare that to the alternatives. A fall into forest canopy is close to hopeless, a fall into water is completely hopeless, and a fall into a suburb produces one roof strike and nothing else. Douglas County is, as strewn fields go, about as cooperative as they come. There is a clock running on the search too, and it is not obvious until you think about what a fresh meteorite actually looks like. A stone that has just come through the atmosphere is coated in fusion crust. A thin, black, glassy rind, usually less than a millimetre thick, formed when the outer surface melted during entry, and then froze again in the few seconds after the glow stopped. That crust is the single most reliable field identifier there is. It is matte black, it often shows fine flow lines from the molten material streaming backwards, and it looks completely unlike any terrestrial rock in a wheat field. It is also fragile and it does not last. Rain gets into it, frost cycles crack it, soil chemistry attacks the metal grains underneath, and within weeks a fresh fall starts developing rust staining that spreads through the interior and contaminates exactly the isotopic measurements you would most want to make. A stone recovered in the first few days is a scientific specimen. The same stone recovered a year later is a curiosity. That is why meteorite hunters move fast, why the radar-derived search maps get shared quickly, and why the American Meteor Society and NASA both publish fall zones as soon as they have them, rather than waiting for a refined solution. In Douglas County in August, the weather is on the searchers' side, dry and settled, but that will not last into the autumn. So say somebody finds one. What does a lab do with it? The first thing is classification, and this is where it gets interesting because there are two very different outcomes. The ordinary outcome is an ordinary chondrite. Chondrites are the most common class of meteorite by a wide margin. They are primitive material, aggregates of small spherical droplets called chondrules embedded in a fine-grained matrix, and their defining property is that they were never melted. They have been sitting essentially unchanged since the solar system condensed 4.5 billion years ago. They are the raw material the planets were built from, preserved because their parent bodies were too small to ever get hot enough to alter them. Finding an ordinary chondrite would mark this event as completely typical and would tell us that the object was a fragment of some undistinguished main belt body that never did anything remarkable. The interesting outcome is an achondrite, and more specifically an head achondrite. Head stands for howardite, eucrit, diogenite, three related classes that are widely believed to come from the asteroid Vesta, one of the largest bodies in the main belt. What makes them different from chondrites is that they melted. Their parent body was large enough that heat from radioactive decay in its interior liquefied it, and once a body is liquid, gravity sorts it. Dense metal sinks to form a core, lighter silicates rise to form a mantle and a crust. That process is called differentiation, and it is the same process that gave Earth an iron core and a rocky mantle. So a diogenite is a piece of somebody else's mantle, a eucrit is a piece of somebody else's crust. These are fragments of a small world that formed, melted, organized itself into layers, and then got hit hard enough to scatter pieces of its interior across the solar system, where they have been drifting ever since. They are rare because most meteorites never melted, which is why what happened this spring was so hard for anyone to shrug off. Back in the spring, in our video on the Lake Erie bolide, we covered the confirmed eucrit recovered from that March 17th event. 9 days earlier, the daylight bolide over Western Europe had produced a suspected diogenite. 2 head falls, 9 days apart from parts of the sky about 98 degrees away from each other, on unrelated orbits. And then the Houston chondrite 4 days after that made 3 recoveries inside roughly 10 days, against a worldwide baseline of about 10 in a year. And I want to underline something about those 2 head falls that is easy to skim past, because it cuts against the simple version of the story. The March 8th event and the March 17th event came from parts of the sky roughly 98 degrees apart. Their orbits were unrelated. They were not 2 pieces of the same thing arriving in sequence. So the spring recoveries do not describe a single stream delivering a single parent body's debris. They describe an elevated rate of large, survivable, differentiated material arriving from more than one direction at once. That is harder to explain than a stream would be, not easier, and it is one of the reasons the anomaly resisted a tidy resolution. Statistics can be argued with. Report counts can be attributed to smartphones. Radiant clusters can be questioned. 3 rocks in 3 laboratories cannot be explained away by anything, because they are objects, and they either exist or they do not. So a 4th recovery in 2026, from a fireball whose direction points into the one unexplained part of the anomaly, would matter. Not as proof of anything dramatic, but as another physical object in another laboratory, in a year that has already produced far more of them than it should have. There is also a process that has to happen before any of that classification means anything officially, and it is more bureaucratic and more interesting than you might expect. A newly found stone is not a meteorite in any formal sense until it has been submitted for classification, examined by a qualified laboratory, given a name based on the nearest named geographic feature, and approved by the international body that maintains the official catalogue. That approval requires that a portion of the specimen, a type specimen, be permanently deposited in a recognized institutional collection. You do not get to keep all of it and still have it count. That requirement exists for a good reason. It means that decades from now, when somebody develops a new analytical technique, there is still material to run it on, held somewhere accessible rather than in a private drawer. A meteorite that never gets classified is scientifically invisible, no matter how genuine it is, and in the United States, on private land, the stone belongs to the landowner, not to the finder, not to the state, not to NASA. Which means that the practical question of whether the Sims Corner Fall ever enters the scientific record depends partly on whether the owners of a few wheat farms in Douglas County are amenable to strangers with metal detectors walking their fields, and on what arrangement gets made. That is not a footnote. A meaningful number of falls are recovered and never studied because the negotiation goes badly. And there is one more measurement, which almost never gets mentioned outside the field, and which is the closest thing that exists to a literal answer to the question in this video's title. While a fragment is travelling through space as an independent body, it is exposed to cosmic rays. Those high-energy particles strike atoms in the outer meter or so of the rock and transmute them, producing specific isotopes that were not there before, at a rate that is known and reasonably steady. Once the rock is buried inside a larger parent body, that does not happen because the parent shields it. Once it lands on Earth, it stops because the atmosphere shields it. So the concentration of those isotopes is a clock. It measures how long the fragment has been flying free, alone, since the collision that broke it off whatever it used to be part of. Run that measurement on a stone from Sims Corner and you would get a number in millions of years. That number is the answer to where did it come from. In the most concrete sense, the question can be asked. It tells you when this rock stopped being part of something larger and started being a thing that could arrive over Washington. Nobody can run that measurement yet because as of this recording, no recovery has been announced. Part 14. What we actually settled. 4 seconds. Let us go back to the 4 seconds and be honest about what we now know and what we only think we know. Known with real confidence. The time to the second. The start point over Soap Lake at 77.9 kilometers. The end point over Sims Corner at 45.5 kilometers. The path 36 miles. The heading due north to within 1/3 of a degree. The entry angle about 34 degrees. The fact that it produced a shock wave that reached the ground and registered on 5 volcano monitoring stations, and the fact that it was not a member of any known meteor shower. Known only as an estimate. The mass, the diameter, and the energy. All 3 back solved through a chain of assumptions, and internally inconsistent by a factor of about 5 when you check them against each other. So what actually happened over Washington? Reading 1, and the one I think is most likely to be correct, is the boring one. This was a routine sporadic fireball that happened to be observed unusually well. Somewhere between 40 and 80 tons of extraterrestrial material reaches Earth's atmosphere every single day. Objects in this general class arrive regularly. Most of them come down over ocean, which is most of the planet. Most of the rest come down over land when nobody happens to be looking, at hours when nobody happens to be awake. The reason you have not heard about hundreds of these is not that they are rare. It is that almost all of them happen with no audience. This one entered over a populated corridor saturated with cameras inside the acoustic range of a volcano observatory during a meteor shower that already had people outside looking up. Under this reading, the only unusual thing about the 14th of August is the quality of the observation, and not the object at all. I want to be clear that I think this is probably the right answer, and I'm not going to pretend otherwise to make the video end better. It is worth putting a number on how quiet that background usually is, because it makes the point better than adjectives do. 40 to 80 tons a day sounds enormous, and in aggregate it is. But almost all of that mass arrives as dust, particles too small to produce a visible trail at all, settling continuously and invisibly onto every surface on the planet, including the one you are sitting on. The visible fireball population is a rounding error on that total, and the population that penetrates far enough to be heard from the ground is a rounding error on the fireballs. By the time you get to objects that generate 250 reports at 1 in the morning and register on volcano instruments, you are at the far thin end of a very steep distribution. That steepness is exactly why the 2026 numbers were worth arguing about in the first place. When events are rare, small absolute changes look statistically dramatic, and telling the difference between a real shift and an artifact of counting is genuinely hard, which is what the whole year's dispute has been about. Reading 2 is the one this video has been building. Under this reading, the object is one more data point in a directional signal that nobody has explained, from a year that produced 2 independent 4 sigma radiant concentrations and 3 meteorite recoveries in 10 days. Not proof, a data point. And critically, the test of reading 2 is not this event. One fireball cannot confirm or refute anything. The test is whether the concentration is still there in the second and third quarter data, and that is a thing we will actually find out. Reading 3 is the one I suspect will outlast the story. The remarkable thing about the 14th of August is not the meteor, it is the measurement. The best available reconstruction of an object entering North American airspace at 33,000 miles an hour was assembled out of a weather satellite's lightning detector, 3 cameras that happened to be pointed up, a few hundred members of the public filling in a web form in the middle of the night, 5 seismic stations installed to listen for volcanoes, and a radar built to forecast rain. Not one of those things was built for this. The system that watches the sky over North America for incoming rocks is not a system. It is a set of coincidences that happen to work. And now let us pull the frame back, because there is a scale to this that the local details obscure. Start with the rock. 16 inches, or maybe more, over a wheat field in Douglas County. Widen out, and it is one member of a population of small bodies crossing Earth's orbit continuously, in numbers that run to the millions, almost none of them catalogued, almost none of them catalogable. Widen out again, and that population is being fed. Gravitational resonances with Jupiter have been carving material out of the asteroid belt and throwing it inward for the entire history of the solar system. A slow conveyor belt running on a timescale of hundreds of thousands of years per delivery, and it has never once stopped. Widen out one more time, and the material on that conveyor belt includes pieces of worlds. The differentiated meteorites, the eucrites and diogenites, are fragments of small planets that formed, melted, sorted themselves into core and mantle and crust, and were then shattered before Earth had finished assembling itself. When one of those lands in a field, a piece of somebody else's mantle has arrived on our crust. And widen out as far as the frame will go, and the delivery itself is the story. This has been happening continuously since before the Earth had a solid surface. Every stone in every museum case on this planet arrived exactly this way, by exactly this mechanism, glowing across somebody's sky for a few seconds, and then going quiet. The only difference between the ones in the cases and the one over Sim's Corner is that somebody walked out and picked those ones up. We have always assumed that the sky above us is a settled place, catalogued and accounted for, a background we can safely ignore. But what if the only reason it looks settled is that we have only ever counted the things we were already able to see? For 4 seconds on a Friday morning, a fragment of something that has been travelling since before there were continents on this planet passed over central Washington and came apart. It made a light bright enough to wake people 100 miles away. It made a sound that 5 mountains recorded, and the only reason anybody knows which direction it was going is that a satellite built to watch thunderstorms happened to be looking. Everything else about it, the size, the weight, the energy, is an estimate. The direction is the one thing we actually measured, and that direction points at the single part of this strange year that no statistical analysis has ever examined. There is a version of this story where none of that matters, and I want to give it its due before I close because it is probably the version that is true. In that version, a fairly small rock on a fairly ordinary orbit met a planet, as fairly small rocks on fairly ordinary orbits have been doing continuously for 4.5 billion years, and the only remarkable thing that happened is that a lot of people happened to be looking. No signal, no stream, no pattern, just the background being the background in front of an unusually large audience. If that is what this was, then the honest lesson of the 14th of August is not about the sky at all. It is about us. It is that we now live in a world where a 4-second event over an almost empty stretch of Washington gets reconstructed to 1/3 of a degree within hours, because every driveway has a camera, and every mountain has a microphone, and everybody carries away to report what they saw. That is a genuinely new condition. A century ago, this event would have produced a handful of confused newspaper paragraphs and then vanished. A decade ago, it would have produced a shaky phone video and an argument. But there is a cost to that new condition, and it is the reason this video has been so careful about error bars. When the evidence arrives that fast, the interpretation arrives faster. The numbers that went around the world on Friday morning were preliminary numbers, and 2 of them do not reconcile with each other, and almost nobody noticed because there was no time to notice. Speed of information is not the same thing as quality of information, and the gap between the two is where every bad conclusion of the last decade has lived, which leaves one number outstanding, and it is the number to watch for. The American Meteor Society has more than 260 reports on this event, at least 3 camera captures, and a satellite detection. That is enough to compute a proper trajectory-resolved radiant for event 6582 of 2026. If they publish it, and if it falls inside the Antihelion zone, then a rock that came out of the one unexplained direction of 2026 landed in a wheat field in Washington in August, and the concentration did not end in March. And if it falls somewhere else entirely, then this was exactly what it looked like on the first morning. An ordinary rock on an ordinary night that simply happened to explode where a great many instruments could hear it. That single number decides it, and right now, nobody has published it.